Good day. We are carrying on with the PowerPoint about titrations. We've just wrapped up talking about indicators, and now we're looking at three types of titrations. The first one is strong acid, strong base titration, and we get a pH of 7 at the equivalence point. And that's because we make a salt that does not hydrolyze, because the salt, the positive ion and the negative ion both came from strong acid and strong base, and therefore they can't hydrolyze. So we choose an indicator that has a transition point near 7. So what we're saying here is HCl is our strong acid. It supplied the chloride ion, and the chloride can't hydrolyze. And the sodium came from the strong base sodium hydroxide. So sodium we know can't hydrolyze. So we make a salt that can't hydrolyze, and we end up with a pH of 7. So it's a graph page 569, something like that. And I've chopped it out to give you some idea of what it's going to look like. So in this case, and they haven't put numbers on the side, but this would be the pH, probably up to around 14. And we can see we're starting with the base and we're adding acid. And this stays fairly flat, so we would actually say this is buffered. But when we get near the equivalence point, the pH plummets. And that's very useful for us. The middle of this graph of where it plummets, that becomes our equivalence point, and that gives us our volume that we added. So right at this point, we should get a very faint color as the indicator change color in the flask, and then it carries on like that. But the whole point of this is that this part here is going to be a pH of 7. So we want to choose an indicator change color right around there. Now, strong acid plus weak base. Well, our pH at the equivalence point is going to be less than 7. And that's because we make a salt that's going to hydrolyze. And it's going to hydrolyze as an acid. So if we have hydrochloric acid as our strong acid and ammonia is a weak base, we make ammonium chloride. Ammonium hydrolyzes an acid, and chloride, we have already reminded you, cannot hydrolyze. It came from hydrochloric acid. So we'll look at a graph like this. And there are things we notice. So we're adding the strong acid to our weak base. And first of all, it's less buffered. It drops more sharply. It doesn't start at a pH that we'd get if we had a strong base. And when we finish, we're not finishing at pH of 7. If we look at the middle here, it's going to be around here, somewhere between a pH of 4 and 5. So we have to choose an appropriate indicator there. Finally, we have weak acid plus strong base, and the pH of the salt we make is going to hydrolyze because it is the conjugate base of a weak acid. So in this case, the pH will be above 7. So we've chosen a strong base, sodium hydroxide, but a weak acid. Sodium won't hydrolyze, but the fluoride hydrolyzes. And when it hydrolyzes the base. And we're told page 573 if you don't like this PowerPoint. Now notice this time it's going upwards. When we do a titration, it's either a strong acid or strong base that we're going to be adding. We never use a weak acid or weak base in our burette, always strong. So again, it starts and it curves up quite rapidly. It's not overly flat here. It is rising somewhat. And when we look here, we say, okay, that's the pH at the equivalence point, and it corresponds in this case to somewhere between 8 and 10. It might be around a pH of 9 in that case because of the fluoride hydrolyzing. So the shape of titration curve can give us a lot of information. Sometimes I won't tell you what type of titration it was, and from the graph you have to figure out, was it strong acid, strong base, strong acid, weak base, or weak acid, strong base titration. And so that's talking about the buffering where it's flat. Where it rises or falls sharply, that's going to be an equivalence point. Small amount of acid or base causes a massive change in pH. And we have a few other things to add. So here we go. You can read that. We'll skip along. Sometimes we have more than one endpoint, and that means we have more than one sharp rise or sharp drop. And that's when we have something that's polyprotic or polybasic. So in this case, we are adding base to an acid, and you can see the acid is H3PO4. So here is our first endpoint, and we're taking the first proton off H3PO4. Now we have H2PO4, and we're going to take off the second. So we have to get to this volume. And you can see from this graph, we never were able to get the third proton off because we had 1, 2 sharp rises. We're definitely adding base because the pH is going up. So that's giving you some sense of this game. So if the graph has more than one sharp fall, then that base being titrated must be polybasic. More than one endpoint as each proton is added to it. And going the other way, this time we're adding acid to a base. Now we see we have sodium carbonate. And so its middle of the fall is right about there. That's a terrible line. And middle of that fall is about there. And so that's putting on the first proton and putting on the second proton. So we're going from Na2CO3. At this point we become NaHCO3. And then at this point we'd be H2CO3. And that's it for this massive video.